Alright, so today I want to talk about standard enthalpy of formation, sometimes called heat of formation. Just to give you a brief outline where we're headed today, we're going to talk about the standard enthalpy of formation, of course. We're going to learn what is meant by the standard state of a particular substance. We're going to learn how to write equations describing these changes, and we're going to do 3 or 4 examples. So when we talk about enthalpy, keep in mind that we're always talking about enthalpy changes. In other words, we describe a process, say A to B, some chemical reaction, and we say, okay, the enthalpy change for this reaction is, say, X. So that X amount of heat, for example, is being given off or absorbed. We're describing the change in heat as we move from A to B. This is much like a mountain has an altitude that's defined with respect to sea level here. So if I switch to blue and draw the water in here, we describe the height of this mountain here, or the altitude of the mountain, by h. So just as we cannot describe the height of that mountain without a familiar measuring place from which to measure, we cannot describe the enthalpy of one state without comparing it to another state. So we always measure enthalpy changes from one state to another state. So just as sea level is a convenient measuring place to measure altitudes from, the standard state becomes a convenient reference place to measure enthalpy changes from. So let's take a closer look at this reference state. The reference state is the most stable form of a particular compound, and it's usually 298 Kelvin, 25 Celsius, 1 atmosphere pressure. All right. And so, for example, we look at carbon, and you say, okay, what is the standard state of carbon? The standard state of carbon is carbon, solid graphite. And so this becomes our, say, sea level for all carbon-containing compounds. We're going to measure the enthalpy change with respect to this state. And so if you were to do this reaction where you take carbon solid graphite and make some more, or turn it into carbon solid graphite, so you haven't done any chemistry here, you haven't changed anything. And because enthalpy is a state function, we know if we go from state A to state A, the enthalpy change here is 0. So delta HF, or the standard enthalpy of formation for carbon solid graphite, is equal to 0. Well, this is true because we were already at our standard state. So if you're ever curious what the reference state is for a particular element, you can always go back to your appendix into the thermodynamic tables, and you can always find the delta HF value that equals 0 for that particular element. Alright, so that's the first thing to notice. If you're talking about the standard state of a solution, you're talking about a 1 molar solution. And if you're talking about the standard state of a gas, you're talking about a 1 atmosphere of pressure. So keep that in mind. Alright, so let's then talk about standard enthalpy of formation. And all we're doing here is forming a compound from the materials in the reference state. So whenever you see delta HF, this is exactly what you want to think of. Delta HF, okay, stands for enthalpy of formation, and then the little degree sign here indicates that you're at the standard state. Okay, so delta HF naught is standard enthalpy of formation or standard heat of formation. So let's suppose that someone told you that the standard heat of formation, delta HF naught, of CO2 gas is equal to minus 393.5 kilojoules per mole. Okay, what would that mean? Well, this would mean that we were starting at the reference state for carbon and oxygen, and we were forming CO2. We would simply think about a reaction where we form CO2 gas from the elements carbon and oxygen in their standard reference state. So for carbon, that would be solid graphite, as we discussed. And for oxygen, that would be O2 gas. Oxygen is diatomic. And so what we know is that if we were to do this reaction and form 1 mole of CO2 gas, that the standard enthalpy change for this reaction, based on what they told us, would be this minus 393.5 kilojoules per mole. What this means is that if I start here with carbon and oxygen gas at my reference state, that if I want to make CO2, I'm going to move down and release 393.5 kilojoules of heat for every mole of CO2 gas that I make. Alright, so let's get on with the first of our 3 examples. In this case, we're asked to write an equation describing the standard heat of formation for methane gas. So we simply think about a reaction in which we form methane gas. That's always a given. And we form methane gas from carbon, solid graphite, as we've talked about before, and hydrogen gas. So the big thing here that I want to make sure to mention is to make sure, obviously, to balance this equation and also select the correct allotrope for carbon. All right? So we remember that hydrogen is diatomic, so we select H2 gas. Carbon, we've talked about selecting graphite as the correct allotrope. And the other thing is that when you look in the appendix, right, or in a reference that you trust, you'll see that the delta HF naught for this reaction is about minus 75 kilojoules. Okay? What they mean is minus 75 kilojoules per mole of methane. So you're always talking about 1 mole of methane, okay, or 1 mole of any compound that you're forming. Let's try the second example. In this case, we're asked to write an equation describing the standard heat of formation for silver chloride, okay, and solid. So once again, make sure to write the compound that you're interested in over here, write its correct state, physical state, and then just ask yourself, what's the standard state for silver? Okay, silver solid. And the standard state for chlorine, Cl2 gas, another diatomic. All right. We have to balance the equation. We have to balance an equation remembering that the coefficient on the product side, in this case, must equal 1. This is very important, because when you look up the value in the book, all right, and it tells you that the standard enthalpy of formation for this compound, delta HF naught, is minus 127 kilojoules, what they mean is minus 127 kilojoules per each mole of silver chloride that you form. And so we must balance the equation, remembering to always to have 1 mole on the right hand side. That means we do whatever we have to balance the equation so that there's a 1 mole coefficient on the right. So that means we put a 1/2 there for the chlorine. Alright, let's move on to our next example. Alright, so in this next example, we're asked to find the standard heat of formation for ethanol and write the equation. So we go ahead and write our compound over here on the right, and we make sure that we pick the right state, liquid, and then we go on the left and we write all of our elements in their standard state at 25 degrees Celsius and 1 atmosphere pressure. And so the standard state of carbon, as we've said now I think 3 times, is solid graphite. Okay. Hydrogen, H2 gas, and oxygen is O2 gas. Alright, now we have to balance the equation. We're going to balance the equation remembering that this coefficient over here on the right must stay a 1. Absolutely must. So we're going to do what we have to do over here on the left to make that happen. So we put a 2 here. We put a 3 here. We put a 1/2 here. Now we can go back in our appendix and we can actually look up the standard heat of formation for ethanol, okay, remembering to grab the value for the liquid. Okay, the reason I wanted to do this example is to show you delta HF, okay, for the liquid form of ethanol is equal to minus 277 kilojoules per mole. All right, but if you were to look up the delta HF for the gas, okay, for gaseous ethanol, you would find that it's minus 235 kilojoules per mole. So you have to make sure that you get the right one. You have to make sure that you grab the right compound that you're talking about and pay attention to the state that you're asked to find. Alright, so I just want to talk through some of the tips and strategies that we've used in this video to help us use standard enthalpy of formation in the right way. Number one, identify the correct allotrope of the atom in question, remembering to think about things like, is your element diatomic? Okay, and if there's more than one allotrope, then you simply scan through the list in the back of the book, and you find the one for which delta HF equals 0, and that must be your standard reference state. Alright, this next one's very important. This simply tells us that our coefficient on the right hand side when we're writing these types of reactions must be 1. We do whatever we have to do to the coefficients on the left to make sure that the coefficient on the right is a 1, because that standard enthalpy change is reported for 1 mole formation of that compound. Alright, and so again, just with 3, we balance the equation, and we even use fractions if necessary on the left hand side. And again, pay attention to the state of the compound you're forming. It makes a difference whether it's solid, liquid, gas, aqueous, whatever you're talking about. Alright, so in conclusion, today we defined the standard thermodynamic state as a reference state from which we could identify enthalpy changes in subsequently. We learned how to write equations referencing these reactions, okay, going from the standard state to another compound of interest. Alright. Also, you want to look in the appendix or trusted online source to find these values. They're all over the place. They're not hard to find. Alright. Thanks for watching.